Welcome to the Polymath World, and today we are talking origins. We're talking the Big Bang. We're talking how it all started, and we've got someone whose book is hot off the press on this topic. We're joined today by Phil Halper, whose new book, The Battle of the Big Bang, with Niayesh Afshordi. It's so good to have you with us. Hot off the press, really recommend it. If you're really looking for a comprehensive overview of what we know and what we think about the beginning, Phil is your guy. So, Phil, welcome to the Polymath World channel.
Thanks. It's great to be on.
Excellent. So, first off, just tell us a bit about yourself and where this project came from to really investigate all the competing models of the origin of the universe.
Yeah, so I got into this world kind of by accident. I was studying astronomy at University College London, and I was interested in early universe cosmology, and I wanted to learn more about all these different competing ideas for what might have triggered the Big Bang. That was just something fascinating to me. And I kind of like to watch lectures and things like that. And I thought, oh, probably there'll be something on YouTube that will explain some of these different ideas, like Hawking's no boundary proposal or loop quantum gravity, which is a rival to string theory and stuff like that. And there just wasn't anything. And eventually someone suggested to me, well, if you want to watch something like this, why don't you make it? And I thought, okay, why not? Like, how hard can it be? So the first film I made, yeah, I'd read a lot about string theory, and I knew there was this rival theory called loop quantum gravity. So I wanted to learn about that. And I made a film with the inventor, well, probably the key creator of loop quantum gravity, Abhay Ashtekar, and also one of his colleagues, Ivan Aguyo, and they had worked on the loop quantum cosmology. And I didn't really know what I was doing in terms of making a film, but it wasn't very high quality. But yeah, it got hundreds of thousands of views, and people, I thought, are obviously fascinated by this. I am, and I'm not alone. So it just sort of snowballed from there, and I ended up interviewing like a lot of the world's leading cosmologists. And so that was, and then we made this video series before the Big Bang, which is on my channel. So if you want to see that, you can go on my channel, Phil Halper, go on playlists, and you'll see before the Big Bang. And I think we've done like a dozen episodes. But then one of the cosmologists I interviewed was Niayesh Afshordi, and he's a force of nature, because not only has he worked on some of the sort of standard cosmological models, but he's created or been a pioneer of many other different Big Bang models, really fascinating ones. So I thought, I've got to interview this guy. And we hit it off straight away. And we suggested that we should sort of collaborate on a book, because he wanted to write a book. And I thought I had great material from all these interviews, but I thought, well, we could do something quite different to the videos, because the videos are very much explain the science only. And whilst in the book we do explain the science, I thought, wouldn't it be great to sort of tell stories, the rivalries between the scientists, the history of the different ideas and how they actually came about. So the book is much more about telling stories as well as explaining the science. So in the videos, we just explain the science. But yeah, that's how it all came about.
I think this is one of the elementary science questions. It doesn't matter whether you're a child or you're retired. How did it all start, and what happened before the Big Bang?
Yeah.
is one of the great elementary questions of science. Now, interestingly, we had Professor Peter Atkins on here last month, and I asked him what does he think of the biggest questions that he's most excited about in science, and he said this particular issue could unravel fairly soon. So how I mean, without giving all the spoilers away, what's your definitive answer? Do you think there's a strong leading candidate?
Well, that's what we want to try and avoid in the book. We kind of have this theme of, and this is related to COVID, so we wrote this book during COVID, and or at least the first drafts of it. It went through several revisions. And the idea in COVID, was follow the science. And that's right. I mean, we don't dispute that. But also we want to add and embrace uncertainty, because, a lot of these questions, there's a lot of uncertainty. So, and in particular with the Big Bang, we think it's better to be an explorer rather than a believer, because at the moment we don't know what happened before the Big Bang, but that doesn't mean we don't have a shortage of fascinating candidates. And we can say some ideas are plausible or not, but we can't say if any of them are right. So I think there are certain themes that sort of pop up over and again. We can go into some of the ideas, but I think it's better to sort of, particularly for people like us, Sam, we don't have to decide what's the best candidate. We let nature tell us. That's the really important thing, I think. Nature will tell us, hopefully, if she's kind, which is the right model of the Big Bang. And at the moment, then the idea is for us to explore the possibilities, see their strengths and weaknesses. Because I think a lot of these ideas, they have a lot of strengths and weaknesses. I don't think there's any that don't have a foot in both of those camps. There are advantages and disadvantages, and that's what we try and do in the book. Just pull them out.
Yeah, I think there will be a crowd out there who will be quite surprised because you've got relativity, and it works so well, and it solves so many problems, and it's so accurate. And then you've got George Lemaitre and Alexander Friedman who just take Einstein's maths and apply them to the cosmos and go, there you go. It's 13.8 billion years ago, started with a Big Bang, done and dusted. So what's the problem with that?
Right. Okay. So basically, first off, back in those days, there were sort of early ideas of a singularity. This is because you couldn't think, okay, the universe is expanding. So if we wind the clock backwards, it's contracting. Why can't it just contract forever into the past? There's nothing wrong with that logically. Well, it turns out there are theorems that say you can't do that. You'll reach in a finite amount of time what's called a singularity. So this is something where the density, the curvature, the temperature, the pressure of the universe all go to infinity. And basically the sort of trajectories of particles sort of come to an end. They have endpoints. So that tells you there can't be anything before the Big Bang. Now, but why then are we writing a book for what might have happened before the Big Bang? Well, the answer lies, let's go back to those early singularity theorems. It turned out that they had very unrealistic assumptions. So they couldn't really be trusted. Then in the 1960s and 70s, Penrose and Hawking came along and made these ideas much more robust. And they showed that a lot of the simplifying assumptions didn't really matter. You could relax those and there'd still be a singularity. So that was a big, big breakthrough. But even the Penrose-Hawking theorems have assumptions. And we unpack what those assumptions are in the book. But why don't I just pick two for now? There are actually four that we go over in the book, but just for sort of brevity, I'll just mention two. So one is that they assume that gravity is always attractive. And that seems sort of like a very reasonable assumption. I mean, what goes up must come down, right? I mean, it seems extremely reasonable. Can't fault them for making an assumption like that. But it turns out that in 1998, we discovered that the universe is accelerating in its expansion. And what that shows you actually is that gravity is not always attractive. That is a repulsive gravitational term in the Einstein field equation. So, and similarly, there's another idea which is hotly debated, and we go over the debate in the book a lot, but that's something called inflationary cosmology. That also gives you a repulsive gravity term. So it turns out that one of the assumptions in the Penrose-Hawking theorem is basically wrong. The other one that I think is the bigger focus, is really the key, is that they assume that general relativity works in every condition. Now, just like Newton works in a lot of conditions, I mean, you can send rockets to the moon just using Newtonian gravity. You don't have to worry about Einstein at all. So similarly, Einstein's gravity, works in a lot of conditions. But I think almost everyone in cosmology and fundamental physics thinks that when you get to the extreme energy conditions of the Big Bang, you're going to need to modify Einstein's equations with quantum effects. Because we've got these two pillars of modern physics. We've got quantum mechanics, which is, if you like, the physics of the very small, roughly speaking. General relativity, you can think of as the physics of very big. And they actually contradict each other.
Yeah.
But for the most part, these contradictions don't matter. I mean, the quantum effects of a galaxy are just nothing, right? And similarly, the gravitational effects in subatomic physics are also just nothing. They're just, well, negligible, shall we say, to be more precise. And so we can just ignore that conflict. It doesn't matter for almost anything that physicists look at. But when we get to the Big Bang, it's not the case that we can just ignore it. So we need this quantum theory of gravity. And so a lot of people think that the singularity is an artifact of pushing Einstein's theory of gravity beyond its domain of validity. Just you can push Newton's theory beyond its domain of validity and you will get the wrong answers. Just like the orbit of Mercury is the classic example. You calculate the orbit of Mercury using Newtonian physics and it does not match observations. It's wrong. No. It's the reason is because you've pushed the theory beyond its domain of validity. Mercury is really close to the sun, so the really strong gravity effects suddenly become relevant. If you were looking at the Earth, that you're far enough away from the sun that you can just ignore relativistic effects, but for Mercury you can't. So similarly, we think the same is true for the Big Bang, that you need this quantum theory of gravity. And what's happened, the sort of quiet revolution that's been going on over the last 2 decades or so, which is why we think the book's relevant, is that whilst we don't have an agreed upon theory of quantum gravity, there aren't like thousands of candidates. There's probably only like half a dozen that people sort of pay much attention to. And people have developed them enough that they think they can analyze the Big Bang with them. And what is a common theme is that the Big Bang was not the beginning, both in string theory and loop quantum gravity and different approaches. They seem to resolve the singularity. Now, of course, these theories are still works in progress, so we don't want to overpitch this. But the fact that it just keeps popping up over and over again in different approaches, that the Big Bang wasn't the beginning, I think has at least led us to conclude not that the Big Bang definitely wasn't the beginning of time. It still might be, right? But that we can't trust these theorems anymore. And so we have to sort of throw away the confidence that we had that the universe began at the Big Bang.
That's very interesting. And the timing of your book is quite prescient, I think. I was driving around with a NASA astronaut a couple of years ago, Tony Antonelli, and he said to me, I think the Big Bang is not long for this world. And I said, that's very interesting you'd say that, as a NASA astronaut. And he said, well, there's just a lot of problems that I think are going to turn the corner fairly soon. But he added this line. He said, I think James Webb is going to help us rewrite the book on the beginning. So I just want to interject here. How much has the James Webb Telescope and new data that's come in informed your research, or is this still sort of just an?
I think actually I would focus on a different telescope. Actually,
yeah.
I think Webb is very interesting. Of course, it's an incredible piece of science. But one thing I want to caveat things with the idea what your astronaut said: the Big Bang is not much longer for this world. It depends on what you mean by Big Bang, and this is something we put out right at the beginning of the book. That you can think of 2 different definitions of the Big Bang. One we call the hot Big Bang, and the other one we call the Big Bang singularity. Right. So, and in fact, we surveyed physicists on what they think Big Bang means. And I think this is really fascinating and I think should get more attention. So we went to this big conference in Copenhagen of leading physicists, and we did like a survey of like 12 controversies within physics. So what's dark energy, what's dark matter, what's the right interpretation of quantum mechanics, all these sorts of controversies that exist within physics. And there was only one topic out of the 12 that the physicists actually agreed on, where we got more than a majority view for one answer. Wow. And that was that when we defined we asked them, what do you mean, but what do you think the term Big Bang means? So we gave them, is it the theory that says that there was a beginning of time? Is it the theory that says there was a singularity? And they all plumped, well, not all, the majority plumped for, it's the theory that says the universe evolved from a hot, dense state, and it says nothing at all about whether there was a beginning of time or not. So it just says the universe evolved from a hot, dense state. And that, I think, is permanent. We are not going to revise that. There's overwhelming evidence for that. That is not up for debate, in my opinion. But the idea that the Big Bang is the beginning of time, that very few people voted for that. Certainly singularity, even less. So that, I think, yes, that's up for revision. That's up for change or discarding even. But evolution from a hot dense state, no, I don't think that is. Now, I said there's another telescope that's very relevant here.
Yeah.
That I think has really shaken things up, and that is DESI. So DESI is the dark energy spectroscopic instrument, and they studied dark energy, and they found something absolutely mind-blowing, because everyone assumes that the thing that's accelerating the universe is what's called a cosmological constant. And that tells you the universe can never recollapse. So certain versions, not all versions, but certain versions of a cyclic universe are kind of ruled out by this. And the fate of the universe means it's going to be what's called a heat death. So it's a weird term because it's not a death by heat, but maybe it's a death of heat.
Yeah.
The universe just gets colder and more diffuse forever, basically. But what they found was dark energy is not a constant. It's changing over time.
Gosh.
And if it changes over time, then all bets are off for the future of the universe. It could go negative, who knows? And so actually the old version of the cyclic universe with an expansion collapse, that sort of thing, is back on the table. Now, that's the results from DESI. There are other results that also kind of hint at this, maybe. So I think the evidence is growing that dark energy is not a cosmological constant. Now, having said that, when you get new exciting results in physics, you always have to be very, very cautious. So like anything, it could go away. We have to be really careful. And this is not like an established fact that dark energy is changing over time. This is a new tentative finding that may or may not get confirmed. But there's lots of new projects that I think will either confirm or deny this. And so to me, that's the most exciting thing that's happening right now. In the book, we talk about more exciting things that will happen in the future. But I think for right now, this is the finding that's most rocked the cosmology world.
That's amazing. And of course, your book, without spoilers, will have plenty to say about the end of the world as well as the beginning of it.
Yeah,
As a
because
result of these
some
things.
models like a cyclic model. So what's the end, is related to what's at the beginning. But our book is definitely about the Big Bang and not the far future of the universe. But yes, some of the models are cyclic. And not all cyclic universes have this expansion contraction. There are other versions that don't have this. So they wouldn't be affected by this.
No, of course.
If it turned out to go away, I should say, that it turned out not to be a genuine result.
Yeah. I'd love to ask you about some of the people you got to speak to in this. So you spoke to Stephen Hawking.
That's right.
Incredible, absolutely incredible.
Yeah.
You spoke to
Yeah.
Sir Roger Penrose, Nobel Prize winner, and you spoke to
Yeah.
Alan Guth, who, it will not be as popularly known as the others, but is obviously a huge name in this field. So what did they have to say about this? Why don't you start with Stephen Hawking?
Well, actually, why don't I just say something they all agree on, because they all have different
Yeah.
ideas about the Big Bang. But what they all agree on is that we need a new theory of the Big Bang. So nobody thinks that there's like just a singularity and that's it. Penrose and Hawking, who came up with these singularity theorems, or the robust versions of them, I should say, they don't believe that. And Guth thinks the universe is eternal into the past and future. So yeah, these are like the three biggest names in cosmology, I'd say. And that what's interesting is that they all agree that the Big Bang was not necessarily the beginning. Now, they don't all agree on what is going to sort of be the new description, if you like. Penrose and Guth in particular, I hosted a debate between them because they've got very different conceptions of the Big Bang. So let's start with Hawking, right? So Hawking agrees that we need a quantum description of the Big Bang. And in fact, I guess you can think of inspiration that he had, because if you look at a black hole and you describe it just using general relativity, what you find is that it violates the laws of thermodynamics. So do we really want to throw away the laws of thermodynamics? That's because nothing can escape a black hole according to general relativity.
Yeah.
So therefore, black holes violate the laws of entropy, because if they're entropic objects, they should give off heat, right? But if nothing can escape a black hole, then they can't give off heat. So what Hawking did in the 70s was say, well, maybe there's a quantum way out of this problem. So famously, he showed that black holes actually radiate, and this is called Hawking radiation. And he did this using quantum mechanics. If you didn't put quantum mechanics into the mix, then you wouldn't get this answer. So he thought, well, okay, maybe the Big Bang singularity is similarly, an artifact of not using quantum mechanics. So he teamed up with Jim Hartle, and they came up with this proposal called the no boundary proposal. And there, the idea is that when you get to the Big Bang, instead of having 3 dimensions of space and 1 dimension of time, you get 4 dimensions of space and no dimensions of time. So that's kind of their idea. And in the book, we go into more detail about it. And there's plenty of controversy about it, whether it's actually a valid model and so on. But that's their view. Now, actually, what's interesting is that I think Hartle and Hawking didn't actually agree on quite how to interpret this. I think Hawking saw it as a sort of universe from nothing idea, but I don't think Hartle saw it that way. And so there's controversy as to how you should think about the no boundary proposal, which is what their proposal's called. Now, Penrose has a cyclic model. So he thinks we can get rid of the Big Bang singularity actually without using quantum mechanics, that there's another effect that we can sort of think about. And that is, if you go back to the Big Bang, the idea is that you couldn't build a ruler or a clock. The temperatures would be too extreme to do that. And if you can't build a ruler or a clock, then the notion of scale loses its meaning. And so the universe becomes what's called conformally invariant, which just, that's a technical term, but in plain English, it just means that we don't care about sizes, but we do care about angles. So think of it this way. Imagine a triangle, right? You could describe the size of the triangle, right? But you could also describe the angles inside the triangle. So on a flat plane, they add up to 180 degrees. Now, double the size of the triangle. The size changes, obviously, because you've doubled the size. But the angles haven't changed. They don't care what the size is. So there are certain things that don't care what the size is. They're conformally invariant, is the term. So the idea is that the Big Bang becomes conformally invariant. And then you get rid of the singularity. It turns out it doesn't exist in this conception. So then you can ask what came before the Big Bang, which you couldn't do beforehand. And now you don't use any quantum effects at all. And then Penrose thinks it's cyclic. Basically, if at the end of the universe, it would also become conformally invariant. So it cycles. There's another version that we talk about in the book that uses this conformal invariance. And that's even more mind-blowing because the idea is it forms like a time loop. And so you basically go forward in time, you end up at the start and you just keep going and you just end up back where you started. So it's a bit like the movie Groundhog Day. Basically, the universe is in the movie Groundhog Day, effectively. So that's Penrose's idea, this conformal invariance. The time loop is not his idea. That's actually my colleague, my co-author, Niayesh Afshordi. And then Alan Guth is, he's this proponent of inflation because inflation was basically his idea. There are other people that worked on it, but he was the one that really, I think, not only came up with it, but more importantly, he realized it could fix various problems in cosmology. And that was really mind-blowing that it could do so many things. But inflation is thought to lead to a multiverse. And this is eternal. Now, is it eternal in the past and the future? That's up for debate. But it's at least eternal into the future. There you go. There's sort of three ideas, if you like, proposed by the biggest names in cosmology, and all of them are pretty mind-blowing.
Yeah. You've brought in a couple of terms that I was looking forward to us getting into, and I wonder if you can just define them for the general audience so that they can get excited about these ideas. So why don't we start with the cyclic universe, because you've come up with that a few times, but also the idea of a bouncing universe and a cyclic universe. And can you just
we should distinguish between the two because they're not necessarily the same. You could have a cycle that never bounces, and you can have a bounce that doesn't cycle. You could have a cycle that bounces, right? But people kind of think these two are the same thing. And I saw, like yesterday, like a professional cosmologist get this wrong. He was on Neil deGrasse Tyson's podcast, and he just got it wrong. He's confused too.
Okay.
So All right, so let's distinguish between the two. So let's just say what a bounce is first, right? A bounce is the idea that if you go back to the Big Bang, the density gets higher and higher and higher. For a singularity, it goes to infinity. The bounce says no, it can't go to infinity. There's a maximum density. And when you reach that maximum density, you've just flipped the sign of gravity and it goes from being attractive to repulsive. So if you squeeze something too much, it'll bounce out, right?
Yeah. Gotcha.
So that's basically the idea of a bounce. Now that could be a cyclic universe, but it doesn't have to be. It could be, you could have what's called an hourglass universe. So the idea is, if you just think of our universe expanding to infinity, right? Now just put a mirror on that universe. What would it look like? It'd look like an hourglass, right? So you'd have a contracting universe and an expanding universe sort of glued to each other. And in the middle would be like this quantum gravity area, perhaps, where this bounce effect kicks in. And there's something very analogous to this in stars when they collapse. So if you think of a star, when it starts to collapse, it gets denser and denser and denser. Now, for certain stars of a certain mass, there's a new effect that kicks in. It's called electron degeneracy pressure. You don't need to worry about the technicalities of what that is. All you need to know is that it's a new effect, that it's not described in classical physics, but comes about through quantum physics. And that actually stabilizes the star against collapse. Now, if the star's big enough, even that effect will not be enough and it will collapse into a black hole. But for stars with a less mass, this new effect is enough to stabilize it. So similarly, like the idea of this big bounce is that there's maybe some quantum effect, there's this quantum gravity regime that will stop there being a singularity and cause it to bounce back out. So it doesn't have to be cyclic. It could just be an hourglass, one contracting region, one expanding region, both infinitely long. So that's a possibility. Cyclic universes, obviously, you could have something like that, right? It bounces and then it expands and then it contracts and then it expands. Now, as we said, for that to happen, dark energy would have to flip its sign, become negative.
Yeah.
And if it's a cosmological constant, which a lot of cosmologists think it is, then that's not going to happen. But it doesn't have to be a cosmological constant. We don't know that it's a cosmological constant. When you hear documentaries like Brian Cox saying, we know the fate of the universe, I mean, to me, this is just wrong. It's just completely wrong. Like, we don't know the fate of the universe. That is, if dark energy is a cosmological constant, then yes, we know the fate of the universe. And people were looking at dark energy, well, it looks quite like a cosmological constant. So probably it is. But, it might not be. It might be something that changes over time. And there should be a lesson, I think, from the history of cosmology that these commentators haven't learned, which is people thought the cosmological constant was zero.
Yes.
Right? Up until 1998, they thought it was zero. Why? Well, it looked like it was zero. It looks pretty close to zero. So it's probably zero, But it turned out, it's very close to zero, but it's not zero. Similarly, it looks like a constant, but just because maybe it isn't. We have to get more data, and we shouldn't be overly confident about, first look looks quite like a cosmological constant, so probably it is one. Well, it might be one. I'm not saying it isn't one, but it's way too premature to say that it is. We need to do much more work, study it in much more detail before we can have that kind of confidence. And that we've started doing that, and actually it looks like it's not a cosmological constant. But again, don't be too confident. It may end up being one, right?
Yes.
So there are other versions of cyclic universe that don't require this. So like Penrose is a great example. It's not the only one actually. But cyclic universe doesn't have to have a bounce, and a bounce doesn't have to be cyclic. But obviously, the classical notion of a cyclic universe, bounce and contract, expand, contract, expand, contract, that is, bouncing and cyclic are the same in that version.
I must confess I'm quite aesthetically attracted to this, because anything that avoids the universe coming to a cold dead end and that being it, I quite like. But with all due respect to Brian Cox here, we know he's a national treasure, just like Sir David Attenborough and others. Right. It shows that we should hold these things a lot more loosely. A lot of these truth claims. And
well, I think the science of what we're talking about, I think, is a lot more uncertain than the science that David Attenborough is talking about. That's really well established, and this stuff is a lot more uncertain, and we need to be aware of that.
Let's talk about black holes here. People are terrified of these things. I think people are terrified of the fact that there's one sort of in the middle of our own galaxy. But the idea of the relationship between black holes and the beginning of the universe is something a lot of people
Yeah.
won't have heard much about. So why don't you
No.
unpack
Yeah.
that for us?
Yeah. Yeah. Okay. So a black hole has a singularity, and so does the Big Bang. And in fact, when Hawking did his PhD, what happened was Penrose showed that there were these singularity theorems that were much more robust than was imagined. In fact, the early version of the singularity theorem before that was from Oppenheimer and Snyder. And if you've seen the movie Oppenheimer, there's a scene where they're handing out a paper about black holes. What they don't tell you in the movie is that it's the paper showing there's a singularity inside a black hole.
Wow.
But their version of the singularity theorem assumed that the star collapsing was spherically symmetrical, and that is not true. Stars are not spherically symmetrical. So a lot of people thought, well, this is just an unrealistic assumption. So, if we had a more realistic description, we wouldn't have a singularity. And then what Penrose showed in the 60s was that you could drop that assumption of spherical symmetry and you still get a singularity in the black hole. It doesn't matter. And then what Hawking did was he took the Penrose theorem and said, let's apply it to the Big Bang. So there's clearly there's only two places that we know in the universe, as far as I know of. Maybe someone knows of something else, where we think there's a singularity, in the black hole and a Big Bang. I say where there's a singularity in general relativity, given certain assumptions. So the temptation is to think, well, maybe these are the same. And if, like we talked about, the Big Bang being replaced by a big bounce, or the Big Bang singularity being replaced with. So maybe the same happens in a black hole. So if you went into a black hole, maybe it would give birth to a new universe. And there's variations on this idea. My co-author, Niayesh, had developed one that got the front cover of Scientific American.
Wow.
And there they showed that they could actually replace this idea of inflationary cosmology, which is this rapid period of expansion that solves lots of problems in cosmology, that's very, very popular amongst cosmologists. They showed that actually you could sort of replace inflation with this idea of a black hole giving birth to a new universe. But their black hole has to have one more dimension of space. So do you want to bite that bullet and accept that assumption? So that's their version of the idea. But there are other versions. One that I'm particularly intrigued by is developed by Lee Smolin, who's just had his 70th birthday, and they're doing a big festival at the Perimeter Institute, Lee Fest. So his idea is called cosmological natural selection. And so here the proposal is that when a black hole gives birth to a new universe, it inherits the property of the parent universe, but with a slight variation, just like when you have a child, it inherits your properties, but with slight variation. So the idea is the constants of nature would subtly change, maybe a little bit, but from the parent to the child. And then there would be a version of Darwinian natural selection, because the universe that has the most black holes will have more progeny. So and what makes black holes? Well, stars. So you want a universe that makes stars. And so this addresses an issue called the fine-tuning problem. People in the sort of philosophy of religion world call it the fine-tuning problem. Actually, in physics, they tend to call it the anthropic coincidence problem.
Yeah.
But the issue is, well, how is it that the constant nature are so delicately fine-tuned for life? Well, we've had this problem before, haven't we? How is it that the genes are so well designed, if you like, for functioning living organism? If you just threw genetic material together randomly, you're not going to get a functional organism. The answer is, as Darwin showed us, is that there's a selection principle. They weren't thrown together randomly. Doesn't mean there's any kind of intelligent designer. We don't need that. All we need is some kind of selection principle. And Darwin gave us a selection principle, which is sort of reproductive fitness. So what Smolin suggests is that there could be a reproductive fitness for the universe, but for that to work, you'd need some mechanism for the universe to reproduce itself, to have children, if you like. And the idea from Smolin is that it's black holes, that they have children. Now, what I find particularly intriguing about this is that there's a quantum gravity theory called causal set theory, and some scientists working in causal set theory sort of showed that actually it seemed to give us this story of cosmological natural selection. And causal set theory actually predicted dark energy 10 years before it was discovered. A lot of people don't know this. A lot of people think quantum gravity theory has never made any predictions that have ever been tested against the data. But again, not true. Causal sets predicted this 10 years beforehand. So in some sense, then, there's some contact with the experiment. Now, it's a little bit tenuous because the prediction, I don't want to overblow it. The prediction is what's called a heuristic prediction. It's not like super precise. It's like a rough sketch of an idea.
Right.
And then they said that there should be a small value for the cosmological constant. And in fact, their model predicts it changes over time. So even better, if DESI turns out to be right. If it turns out to be wrong, not so good. But so that's super exciting. And black holes maybe have a motherly side to them.
Yeah, it's amazing. They could be the key to this in the end. People tend to think of them as destructive, not creative. But it is very exciting. I mean, I'm conscious we've got about 20 minutes left, and I absolutely want to make sure that we address something of multiverses and something of string theory, two other tantalizing things people get wrapped up in. Let's start with multiverses, because I had the pleasure of moderating a discussion on science and religion between you and Professor Paul Ewart earlier this year, and you sort of dropped this fabulous tease that I was really interested in during it, that we might even have some tangible evidence for a multiverse from studying the Big Bang. So tell us about multiverses. You're free to take it however you want.
Sure. Well, obviously it's a controversial topic within physics, and in the book, we go over the pros and cons of this idea. There's a lot of, I think, powerful reasons to think we live in a multiverse, but there's also problems with the idea. So let's sort of go over both of them in the time that we have. So first of all, why should we think we live in a multiverse? I mean, there are general ideas, you could say, just philosophically, and say, well, hey, everything we see in the universe has multiple realizations. We see people being born, and there are lots of people. We see stars being born, and there are lots of stars. We see galaxies being born, and lots of galaxies. Why shouldn't the Big Bang just have lots of Big Bangs as well? Maybe that should be the default assumption. I mean, it's hard to know what the default assumption should be, because that is what we see in every other case. I mean, could be Big Bang as the exception, though. Maybe it was a unique event and there's no other Big Bangs. Possible, but, should it be the default? I don't know. But when inflationary cosmology came along in the late 70s, early 80s, what this is a theory that, or a class of theories, we should say, that has this very rapid expansion of space. So people talk about it doubling in something like 10 to the minus 37 seconds. It's just insanely fast expansion rate. Now, this expanding space, when it's undergoing inflation, is unstable, so it decays. And when it decays, it heats up the universe and creates like our Big Bang. So in fact, inflation now you can think of, if we define the Big Bang as the hot Big Bang, that we talked about those two definitions, then inflation happens before the Big Bang. It doesn't happen after the Big Bang. So in that sense, in fact, Alan Guth said it was a prequel to the inflation, to the Big Bang, sorry. But the interesting thing is, because it's a quantum process, it undergoes a decay like a sort of radioactive particle decays. So half of it decays at once. But now we can ask, what's happening to the other half that hasn't decayed? Well, it's undergoing exponential expansion, right? So half of space decays, you get our Big Bang universe. The other half is exponentially expanding. And as long as that exponential expansion is faster than the exponential decay rate, then in fact, the amount of inflating space can never go down. It can only go up, basically. It just goes on forever, making another pocket universe, another. So basically, it makes an infinite number of universes. That's the multiverse. Now, this is related to string theory, because string theory seems to predict that you can have different universes with different constants of nature, as it were. Now, again, there's some debate about that, but this is called the landscape of string theory. But you want something to sort of populate the landscape. And eternal inflation, which is this idea of inflation going on forever, it's called eternal inflation. That would sort of populate the landscape. And so each universe would have different values for the constants of nature. And now I think there's sort of two two or three ways you could say there's evidence for this. So remember we said before about Smolin's idea and how causal sets had predicted the dark energy 10 years before it was discovered. Well, it turns out Steven Weinberg, perhaps the most famous physicist of last few decades, well, within the field, maybe not as a household name like Stephen Hawking, but he was
a lot of people know the first 3 minutes.
yeah,
We've
very
written in his
famous
book.
book. Yeah, but he won the Nobel Prize in physics, and was considered like probably the leading theoretical physicist of his age.
Yeah.
And he also predicted dark energy 10 years before it was discovered, but he did it on the basis of the multiverse. He basically said, look, if there's lots of different universes, then actually there won't be a zero value for the cosmological constant. It will just be big enough that we could live in, So that would give you a small value, but not necessarily zero. And that's exactly what we found. So that's one sort of piece of evidence that you could bring. If I, with my multiverse hat on, that's what I would sort of use. Okay. The second thing I would use is that a lot of cosmologists think that we have evidence for inflation, and in fact, there are different inflationary models, but it seems like a reasonably generic outcome of almost all inflationary models, but not all. There are, you could tweak a model of inflation to maybe not generate a multiverse. But the one that was favored from the data strongly favors the multiverse. So that's another way you could say there's evidence for this. Third way you could say there's evidence for this is there's like some anomalies in the cosmic microwave background. So the cosmic microwave background is the oldest light that we can see, and people might be familiar with, they can sort of make maps of it, and it looks basically like a sort of speckled egg. And those speckles are the sort of hot and cold spots. So there are some bits that are slightly hotter than others, some bits slightly colder than others. Roughly, it's very uniform. I mean, to 1 part in 100,000, it's perfectly uniform. When you get to beyond that, then you start to see these hot and cold spots. So there's this bit of the cosmic microwave called the cold spot, which is like, it seems to be way too big and cold for what we might expect. So there's a suggestion that could be like from two bubble universes colliding. Now, we don't know that it's that. What we want to do is maybe trying to rule out some of the less exciting ideas for what could generate the cold spot, and some of them have been ruled out. So the multiverse impact is still on the table, shall we say? We don't know if it's that, and obviously we need to be very cautious. But so there are some sort of observational impacts, if you like, so, ways you could say we have observational evidence for this. Now let's take our multiverse hat off and let's go with the critics. So I think the strongest criticism of this idea is that maybe inflation isn't actually even true. There are alternatives to inflation. We go over them in the book. So you could, that bouncing model that I said was cyclic, that version of the bounce, if you like, or that version of a cyclic universe. There you can get rid of inflation altogether, and then maybe you wouldn't have a multiverse. So that's one way to sort of challenge this idea. Another way is maybe we've misunderstood inflation. We are extrapolating our physics to extremely high energies. So maybe we're overly extrapolating. That's a possibility. It's possible that we've misunderstood inflation. I think I've interviewed most inflationary theorists, and I think it's reasonable consensus that inflation leads to a multiverse. But I will mention Slava Mukhanov. He's a leading inflationary theorist and he thinks it doesn't lead to a multiverse. But I think he's in the minority, right? I mean, most of people who work on inflation, like at the theoretical level, would agree it leads to a multiverse. So I think those would be, if you don't like the multiverse, and a lot of people don't like the multiverse, and one of the things that they don't like about it, and let's stay with our criticisms for the moment, is that, well, if you get this infinite multiverse, then, you get the situation that Alan Guth has his comment that, anything can happen, and it'll happen an infinite number of times, anything that can happen will happen, and it'll happen infinitely many times, I think was the phrase. So now, how do you do probabilities? How do you say what's likely? Because everything is infinite, So now it's not impossible to do probabilities in infinite set theory, but there are complications and difficulties, and I don't think all those difficulties have been overcome. There are proposals for how you might overcome them, but it's certainly a big challenge.
Yes, I
So
thought infinity
hopefully that.
was. I thought infinity was
Sorry,
something.
say again.
I thought infinity was something we were trying to get away from here. Wherever
Well,
possible.
so no, that's a good question. Like, because I think there are sort of certain types of infinities that are unacceptable. Because a lot of people say physicists don't like infinities, but actually that's not true either, because it's really only certain types of infinities that I think they are not happy with. So, for example, if you calculate a value for something that you could observe, like the energy of two particles colliding, and that comes out as infinity, that's unacceptable because you can't measure infinite quantity for something like that. However, if you have something that you couldn't really observe, like the extent of space, for example, I think most physicists would be perfectly happy with saying space is infinitely big, or infinite in duration. That's fine. So I think there are badly behaved infinities, and other infinities are okay. So it depends on the type of infinity. That statement, physicists reject infinities, or if you have infinity in your theory, something's gone wrong. That is a little bit going a bit too far. And actually, there's more nuance to it. Certain types of infinities are rejected, but not all.
Hmm. Now, that a lot of physicists haven't been particularly kind to string theory. But from what you say, a lot of this seems to be a field that's moving pretty fast. So would you just very, very briefly summarize what string theory is and just the extent to how seriously it's taken today?
Yeah. So we did a survey of this as well. We asked people what is your favorite theory of quantum gravity, and string theory was the winner.
Right.
So this idea that string theory has been abandoned might be wrong, but let me give a caveat that might help those that want to say string theory has been abandoned, right? It didn't score particularly highly. It wasn't like, more than 50%. I mean, I can't remember what the number was off the top of my head. But it was the number one of the race, but it didn't get like a majority or even, particularly high score. The highest score was we don't know.
Right.
I think, or no, I think it was no opinion or something like that. I think the majority view is treat string theory with caution. Certainly, we don't know if it's right, but there hasn't been a better candidate that's come along. So there are other candidates, and yeah. So I think what's happened with string theory. So maybe we should explain what it is. So it's a candidate for quantum gravity, and like really briefly, is that you basically replace particles with extended objects called strings, and that has some additional bells and whistles that you need. Like there has to be these other types of particles called super particles or super partners, or a type of symmetry they say is supersymmetry, and then it also needs extra dimensions of space.
Hmm.
Now, what was it really exciting? I think people were super excited about string theory because there was it needs these superparticles, right? This supersymmetry. And there was a whole nother case for supersymmetry that was really exciting. Physicists thought, wow, we've got a whole nother argument that there should be supersymmetric particles. And then they looked for them at the LHC and they didn't find any. Now, that doesn't mean that supersymmetry doesn't exist, but it meant that other independent case for supersymmetry goes away. So supersymmetry could still exist. It doesn't prove string theory is false. But if you like, there's sort of, different ideas all pushing in the same direction. Now that's gone away, if you like. The case for supersymmetry is weakened, right? So I think the shine of string theory has gone away a little bit because we didn't find any supersymmetric particles. So that was a blow to string theory, but it's not a knockout blow, not by any means. I think if you want to deal a knockout blow to string theory, you're going to have to show that either it's like fundamentally inconsistent, or more likely you just come up with something better. And people have come up with alternatives, and they've got their strengths and weaknesses, and a lot of them we could talk about in the book because there's cosmologies that come out of these, like loop quantum gravity is probably the most famous one because it was in the TV show Big Bang Theory, if you remember. The character, Leslie Winkle dumped Leonard because he favored string theory and she liked loop quantum gravity, and she said, how will we raise the children?
Yeah, it's terrible when
So
time gets between us.
yeah, exactly. Yeah. So they've got their strengths and weaknesses, but I don't think any of them have been, supported enough to usurp the king, as it were. So I would say string theory is still the leading candidate for a quantum theory of gravity, but it's definitely lost some of its shine. It's lost some of the excitement. And so people are a little bit less interested in it, I would say. Maybe even a lot less interested in it. That's probably fair.
Well,
But
we'll see
you've
how.
got to get something better if you're going to usurp the king.
Yeah, and we'll see how it plays out.
Yeah.
I'm really delighted to recommend your book. And I encourage the audience to check it out. The Battle of the Big Bangs. The Battle of the Big Bang. Phil Halper and Niayesh Afshordi. It's University of Chicago Press. You can get it in all good places where you would get books. Just before we let you go, a little bit more about where people can find you. I'm so impressed with your astrophotography. It's appeared in all sorts of publications, popular and major news outlets. So tell us a bit more about you and where people can find you and your work.
Right, yeah. So you can go on YouTube. That's where I do most of my stuff, and go on Phil Halper. I do sort of different things on my YouTube channel. Some of it's like philosophy, philosophy of religion, and I do sort of science. So what I would recommend, depending on what you're interested in, go on the channel and just hit playlists, and you see what you're interested in. If you're interested in the cosmology stuff, there's cosmology playlists. I have a show also called the Sci-Fi Show, where it's about science and philosophy, but particularly with philosophy of religion in mind. So I am an atheist, and we have two other atheist philosophers, Alex Malpass and Dan Linford, as regulars on the show. And then if you want to see my photography, I'm on Flickr, so just go Phil Halper Flickr, and you can see my astrophotography. But I do a lot of landscape and wildlife photography as well, so you can find the stuff there.
Yeah, when you're not jumping out of planes or swimming with sharks and whales.
Yeah.
All sorts.
Yeah.
I love it, Phil, because you've got something for everyone, and we're delighted. We're delighted with that. And it's been a delight to have you with us here today. Thank you so much for your outstanding commitment to science communication. It's greatly appreciated, and we certainly need more of it, more good science communication out there.
All right. Thanks very much. It's been a pleasure being on.
Thank you so much for watching. Don't forget to like and subscribe. Stay tuned for more amazing conversations with incredible researchers who are changing the world we live in and driving humanity forward. Feel free to check out my Instagram at polymath_Sam, or go to my website at www.sam-mckee.co.uk.